Let us try to derive an expression for the radius of Bohr's orbit. Now, in order to start with the derivation, you will need first two of his postulates. So, first, let us discuss them. The first postulate it deals with, say, you have an electron which is revolving in a circular orbit in some nth orbit at some distance Rn with velocity Vn. Since the electron is revolving in a circular orbit, it will need some centripetal force. The centripetal force is given by the term mv square by r. Here, this centripetal force will be provided by the electrostatic force that is between the positively charged nucleus and the negatively charged electron, which is given by the expression 1 over 4 pi epsilon naught z e square over r square. Here, Z is the atomic number of this atom. And the second postulate states that the electron cannot revolve in any particular orbit. It has to revolve in orbit such that its angular momentum, that is the mvr term, has to be an integral multiple or an integer times the quantity h over 2 pi. Here, h is the Planck's constant. Now, with these two, we are very well equipped to derive the expression for the radius of nth Bohr's orbit. Let us proceed. So, starting with the first postulate, I can see that I have Rn on both the sides. So, I can simply cancel this Rn with this square term. Taking this Rn onto that side and the MVn square onto the denominator in this particular side, I get Rn to be Z e square over 4 pi epsilon naught MVn square. Now, what we have done is we have written the radius, which is the Rn, in terms of the velocity, but I don't want in terms of velocity. What I can do is obtain an expression for this velocity using the second postulate. Now, in the second postulate, I have a Vn. If I keep the Vn term onto this side and take this n and Rn onto that side, I get nh over 2 pi m Rn. Now, since I need Vn square, I will simply square this Vn square and I get m square, h square over 4 pi square m square Rn square. Now, I can simply substitute this Vn square onto this expression, which gives me Rn equals Z e square over 4 pi epsilon naught m times the quantity m square h square over 4 pi square m square rn square. Now let us simplify this. So I can cancel this 4 with this 4. I can cancel the pi with the pi squared. And I can cancel m with the m squared. And writing the remaining part by taking this onto the numerator, I simply get Rn to be Z e square pi m r n squared over n square h square epsilon naught. Now I can see that I can again cancel the rn with this square term and simply taking these terms onto the numerator and these terms onto the denominator, I get rn, which can be written as rn equals n square h square epsilon naught divided by pi m z e square. So this, my friends, is the expression for the radius of nth Bohr's orbit. Now, as you can clearly see from this particular expression, that most of the terms, such as this h, which is Planck's constant, is given by 6.626 times 10 to the power minus 34 joules second. Epsilon naught, which is permittivity of free space, is simply 8.85 times 10 to the power minus 12 coulomb square per Newton meter square. M, which is the mass of electron, is simply 9.1 times 10 to the power minus 31 kg. And E, which is the charge of electron, is simply 1.6 times 10 to the power minus 19 coulomb. And we all know the value of pi, which is 3.14. Now, if I club these constants together, what I get is Rn equals the h square epsilon naught divided by pi m e square. These are all the constant, and leaving the constant, we have m squared divided by z. Now, this constant they can be represented by a naught. Here, a naught, it is called as the Bohr's constant and is given by 0.53 angstrom unit. So this expression is quite frequently used in numerical problems. Now, if I suppose for hydrogen atom, I know that atomic number equals 1. So I can write Rn as A naught times m square. Or since A naught is constant, I can say Rm is simply proportional to m square. That is, the radius of nth Bose orbit is directly proportional to the square of that orbit number. N is also called as the principal quantum number. Thank you.